So hello world, welcome to this video where I will be attempting to code a falling sun simulation with vanilla JavaScript. So if you like this video, hit the like button and subscribe to the channel if you'd like. And also if you have any questions, suggestions or questions or suggestions for videos that I might do in future, feel free to leave them down in the comments. And if you make anything with this that you might want people to see or you might want me to look through, feel free to leave them down in the comments. So I have a blank VS Code project here, and I will first make my files, canvas, where I'm going to display the sand, the JavaScript file, and the HTML file, and the CSS, of course. Then I will create my HTML template and add the canvas item, the canvas element, give it an ID of canvas. Then I will add my script to this. Then we will move to the CSS again. We don't have to do much here, but select the body and HTML element, give them an overflow of hidden and a padding and margin of 0, so that the canvas doesn't have any white space at the edges, and so that the canvas doesn't overflow of the screen, causing there to be scroll bars at the edge. Then next we shall select the body, give it a background of slightly gray, then we'll give it a width of 100% and a height of 100 of the 100 viewport height, so that it fills the entire screen. Then we will select our canvas and make it fill the entire screen. So now we have everything set up. We can close the CSS file since we are not going to touch it again. Then we will now move to the JavaScript. So here, what I want to do first is select the canvas, then I will select its context 2D, which is like the pen we're going to use to render or draw everything on the screen. Once we have that, we are going to select the canvas and tell it that the number of pixels on your width is equal to the number of pixels in the screen's width, and the number of pixels in your height is equal to the number of pixels in the window's height. So once we are done with that, we can now, let's create a function to draw a grid. So we can create a constant, let's call it cell size. For this simulation, I'll maybe use a cell size of 16, so that each square is 16 pixels by 16 pixels wide. Then we will create a function, let's call it draw grid. We'll see later if we'll really need the grid lines, but for now we can just use it to visualize everything. So draw grid, let's create a for loop for let x is 0, x is less than or equal to the canvas's width, x is x increment by cell size. Then for every iteration of this, we will move the pen to x 0, then we will draw a line to x canvas dot height. So this will draw the horizontal lines, no, the vertical lines, I mean. Once we run it, let's run the function and see if we'll get anything. Yes, before we can see anything, we have to actually draw the lines by calling pen stroke, the pen stroke method. And now we have the vertical lines. Next, we will draw the horizontal lines. We will use a for loop. So if you don't get what this for loop is for, I have another function, another video where I talked about creating a 4-directional grid-based movement video. I'll put it down in the description. But basically what this function does is for okay, let's start at the first iteration. So at the first iteration where x is 0, the pen will move to x0, which is here at the origin. Then it will trace a line to x is 0 and y is the canvas height. Then in the next iteration, it's going to move to x is 32. Then it will trace a line from x is 32, y is 0 to x is 32 and y is the canvas height, and so on and so forth. So for each of this, it will move to the top, then it will trace a line to the bottom until it reaches the edge of the screen. That's how we draw the vertical lines. And for the horizontal lines, we are going to do something similar but slightly different. So for let y is 0, y is less than or equal to the canvas's height, y plus equal to cell size, or y increment by the cell size. So for this, what we are going to do instead, so that we can actually draw the horizontal lines, is we'll move the pen to 0, y, then we will trace a line to canvas dot width y. So this will draw lines horizontally. So the pen will move from y is 0, x is 0, and trace a line to y is 0, x is canvas height. Then in the next iteration, it's going to draw a line from y is 0, y is 32, x is 0, then it will trace a line to y is 32, x is canvas width. So it's going to repeat that process, until it reaches the edge of the screen. That's how we draw the grid lines, the horizontal and vertical grid lines. So once we have that, we are going to create a function. Let's call it update. And we'll actually move this function here and call this function instead. This is the function we are going to use to update everything on the screen. So before we actually draw anything on the screen, we actually want to clear the entire screen so that things don't smear around, so that before the next frame is drawn, everything is cleared on the screen. If you don't do this, everything will sort of smear itself. So I'm clearing a rectangle from the origin of the screen, which is here, pen.clearRect 00, canvas.width, canvas.height. So I'm drawing a rectangle from the origin with the width of the canvas and the height of the canvas, and I'm clearing everything in that rectangle. So we're clearing everything on the screen, then we'll redraw everything after we've cleared the screen. So now I am going to create an array. Let's call it particles. Then let's create a function called add particles, and it will take in, let's say, an event E. Let's say an event E. Then let's check every time a key is pressed. No, every time the mouse is clicked. Every time the mouse is clicked, let's create let's create a variable. Let's call it is drawing, so that we can be able to draw many sand particles at a time. and let's set it to false for now. So when we click the mouse, we are going to set is drawing to true, and when we release the mouse, we are going to set is drawing to false. We don't need that. Is drawing is false. By the way, for those of you who don't know what this is, it's something in JavaScript called arrow functions. You can look it up you can look it up later, but it's basically just a fancy way of writing a function. Since if you don't want to do this, you can maybe switch this to you can basically switch this to this, but it looks cooler when you do this. And it just looks sweeter when you do this. So it's something called arrow functions in JavaScript. They're just functions, but it's a different way of writing functions. You can look it up later. So what I'm basically doing here is when we press the mouse, we'll set is drawing to true, and when you release the mouse, we'll set is drawing to false. So now, when we press the mouse down, we want to run the function called add particles. No, let's call it add particle because you're only adding one. Then we'll pass in the argument e. This argument, we'll pass it down to the add particle function. Then from here, we are going to check. Let's create another object. Let's call it particle position, and let's give it a property x. Let's set it to 0 and a property y, which is 0. Then we can now actually get the actual position for those who just 0 and 0 is just a placeholder. We can actually get the the actual position of the particle, so that when we click anywhere on the screen, we are going to pass that event to the add particles function. Then we can use the position of the position where we clicked, and we can use that to get the position where we're going to add the particles. So particle position is equal to the math.flow. Math.flow is like it's like rounding off in math, but instead when you round off in math, when you have something like 0.1, you're going to move it to 0, and when you have something above 0.5, you're going to move it to 1. But in math.flow, when you have 0.1, you're going to round it off to 0, and when you have anything above 0.5, you're also going to move it down to 0. When you have 0.9, it's also going to be flowed down to 0. When you use math.ceil, which is also another function in JavaScript, math.ceil, when you have 0.1, it's going to move you to 1, and when you have 0.5, it's also going to move you to 1, or when you have 0.9, it will also be rounded off to 1. But for this situation, we'll only use math.flow, so that when we are pressing even at the edge of this particle, it's going to take it that we're drawing in this square and not the next one. That's why we are going to use math.flow. So we are going to flow the e.client x. This is the position, the x position of where the mouse was clicked. So we're going to flow this divided by divided by the cell size, and for the y position of this particle, we will do the same. E.client, instead of client x, we'll do client y, then we'll divide it by cell size. So now we can maybe let's alert particle position, and let's see if it's actually doing what we want. So let's press object, it's actually doing something, but Of course we can't see it, so let's do this. Particle position dot x and particle position y, so that we can actually see the coordinates. So when I press that, okay, 0, okay, let's turn this into an array. So now when I press, for example, the first square here, we can see that we're getting the coordinates 0, 0, and if I press this one, we're getting 37, 0. That's the index of this square, and when I press this one, we will get 38, 37, and the next one might be 37, 37. So yeah, this function is working properly. Now we can get the actual coordinates of each of these squares. So now we can just comment out this alert, or we can just remove it from the code because we don't need it. So now that we can actually get the position of the particle, we can now, let's create or let's push the particle position to not particle position to the particles array. Let's put the particle position to the particle position to the particles array. So every time we click a square, that position is pushed to the particles array. So now we can move to our update function and loop through every particle in the particles array. Particle dot for each particle, we will do this. So for each particle, we're going to begin a path with the context 2D or the pen. Then we will draw a rectangle at the particles X position and the particles Y position, and the width and height of that rectangle will be cell size and cell size. So we're basically going to draw a square. Then we will run pen.fill. Yes, then we'll run pen.fill. So basically what we're doing with this function is that for every element in this particles array which we've added here, when we press a button, we are going to get the position of that particle. Then for every particle that we've added, we are going to push it to this array. So once it's in this array, in the update function, we are going to loop through every particle in that, or every object in that array, and we are going to draw it. That's how we are going to render the squares. So once I press a button here, it should draw a black rectangle, and I am not, yes. So particle.x times cell size and particle.y times cell size. Yeah, there was an issue there. So we are going to get, for example, if the position of that particle is 1, 0, it should be here. So what we're going to do is multiply everything by 32. So it's going to be 32, 0. So it's going to draw the rectangle here. We have to multiply everything by cell size so that they can actually appear at the correct position. So I'm going to press this and there is nothing happening. I'm not sure why. Let me check. Oh, I gave out no. Let me check in the console. The issue. What issue is there? Why am I not seeing anything on the screen? Oh, yes, I know now. So every time we add a particle, let's call update, so that it can actually render everything on the screen. Because at this moment when we are adding particles to the screen, we really don't see anything because we haven't re-rendered everything on the screen. So we'll add a particle, then we'll come here and clear everything on the screen, we'll redraw the grid, then we'll actually draw the particle. So let's run the function now and we should see a rectangle. Yep. So now that we can actually see the sand particles, what I want to do now is actually get them to to fall, or okay, let's actually make it so that we can be able to draw multiple particles at once, or no, let's actually get them to fall first. So once we've rendered every particle, what we can do here is particle dot, no, we can check if, no, let's move out here first. Let's create another constant. Let's call it grid size, and this object will be an object with x and y property again, and it will keep track of the number of segments we can have in our grid, that's horizontally and vertically. So the number of segments we'll have in total on the horizontally or on the width should be whatever we have here, which is math.flow canvas.width divided by cell size, and the y will be math.flow canvas.height divided by width by cell size. So we will actually be able to tell if this is the last. We're going to use this object to tell whether we are at the bottom of the screen. So here, for every particle, we'll check if particle dot y is less than the grid size y, then we are going to take the particle y and add 1 to it. Then once we run this, we really won't see anything. So what I'm going to do is I'm going to set an interval which we'll call update every, let's say, every 0.1 seconds. Yeah, every 100 milliseconds we will call update. I don't really need this now, or maybe I do for the initial drawing, so I'll just leave this here. So once we add a particle, we should see it going downwards. Yep. And when it reaches the bottom, we can see that it stops, because we are checking if the particle's y position is less than the grid size. So now if we drop another particle, we're going to see it going down, but you'll see that they're overlapping. Now we'll have to fix the behavior where they overlap, because these are actually sand particles. They shouldn't really overlap unless maybe it's 3D and the particle has fallen behind the other one, but for this situation it's just 2D, so we have to stop them from overlapping. And how we are going to do that is, how we'll do that, let's create a for loop. Should we create a for loop? Thinking about this. Yeah, let's create a for loop. Let I is 0, and we'll loop through every particle, not using a for loop, not using a for each loop this time, but using a for loop actually. So for let I is 0, I is less than the particle array's length, I plus plus. So for every particle we're going to loop through, every particle. So const particle is the particles I. So for every particle in the particles array, it's basically the same thing as this one, but using a different different syntax. So we're going to check for every particle. If the particle, okay, now since we're using this, we can actually move this up here. we don't really need it down there, we can use it here. So if the particle is at the bottom, then we can just skip this one, continue. We can just skip to the next iteration. But if the particle is not at the bottom of the screen, we will create another for loop. We'll create another for loop. J is less than or equal to the particle. That will still loop through this for loop will still loop through the particles array, and for this one we'll check every other particle. We'll check every other particle. Let's call it neighbor particle. So for every neighboring particle in the array, or for every other particle, which is particles j. So for every other particle, we'll check if. So what we're going to do here is, once we add a sand particle, we're going to check if at the bottom of this sand particle there's another particle. If there's another particle, then we won't move this one square down. So once it reaches the bottom, if we have another particle on top of the particle at the bottom, we won't move the particle at the bottom to the bottom, rather. So we'll check for every other particle. So if the neighbor particle's x position is not equal to our particle's x position, we will continue. We'll just skip this into this loop. And if they're on the same position, what we're checking is if the particle we're checking isn't on the same square as the same x position as our current particle, we'll just skip it, because it can't be at the bottom of this one if they aren't on the same x position. So if they have the same x position and the y position of this particle is just one place below the other one, so that's what we want to check. So if this particle is not on the same x position as our current particle, we'll just skip. And if this particle also okay, let's change this for loop. I'm trying to think here. Well, let's change this into a different way. Yeah, let's negate this and turn it positive. So if the neighbor's particle x position is equal to our current particle's x position, and if the neighboring particle's y position is equal to our particle's y position plus 1, then we will break out of this loop. I think that's going to work. No, it's not. This won't work. Will this work? I'm trying to think here. Okay, let's create another array up here, and let's call it updated particles. No, that's something else. We're trying to check here if I'm trying to see here if the neighbor's x particle is equal to this, and the neighbor's y particle is equal to if this particle is at the bottom of the current particle, then let's create variable here. Let's call it should update. Yeah, let's call it should update, and let's say it's true. So if we have a particle at the bottom of the current particle, then should update will be false. So this basically checks if we have a particle at the bottom of a current particle, then we don't update the next particle, then we break out of the loop and we stop moving. So we'll move down here and let's check if should update, then our current particle's y position will be incremented by 1. I think this should work. There's an issue. Uncaught cannot read the properties of y. Const particles I. So I am being told that there is an issue. Let me just reload this. Stop this interval for a bit and reload the page. So there's an issue here. The thing that I can't access the this should be so I found another issue here. So this should be if the particle is greater than or equal to the grid's y size, then it should just skip to the next iteration and not do all of this. That is, if the particle is at the bottom, then don't actually check its neighbors and see if you should move it down, but just leave it where it is. But if the particle is not at the bottom, then check if it has something at its bottom. That's basically what we're doing. So I saw them telling me something. Cannot read y. Not sure why they're telling me that. What's the issue with y? Update calls. Okay, let's run update. Update moves here. It runs through a for loop. Oh yes, this shouldn't be less than or equal to, it should just be less than, and this should also be less than. Then it should work right now. That was just a minor syntax error, which will actually go out of index. It should actually go, it's going to look for particles that don't exist. That's why it wasn't working. So now once we press it, we should see it working well. Yep. Then we'll drop another particle and it's still passing through the particle below it. So it means that there's an issue here with my loop. So if the neighbor's x position is equal to this current particle's x position, and if its y position is equal to this particle's y position plus 1, then it shouldn't update this function. So what's the issue here? Let's check. So if should update, then you update it. This should be, there's a particle here and there's a particle at its bottom. Particle.y is equal to particle y plus 1. Not sure why this isn't working. I think it should be working, but you know, when you're coding and an issue appears, most of the time it's usually your fault. So I'm trying to look through this bug, through this, and find out what the bug is. Should update is true. Let's try let's try console logging this. Let's try console logging. Let's try console logging this when this is true, or alerting. Yeah, let's alert, let's say like hello, if this condition is ever met. So this condition is never met for some reason. Not sure why this isn't working. Xj, for let j is 0, j is less than the particle length, j incremented by 1. So for every particle So after looking through this, I finally figured out the issue, and the issue is this syntax. I was using particle length, and particle really isn't an array, it's an object. I'm supposed to use the particles array, which is here, but I was instead using the length of this, which was an invalid property. That's why it wasn't working. So let's run this again, and it should work. Yep. So we basically have our falling sand simulation, and now what we can do is let's add the functionality to draw multiple sand particles at a time, and for that we will do this document on mouse move. When we move the mouse and is drawing is true, if we're moving the mouse and we are drawing, then we should add the particle. We should add a particle to the position. So we press down and we move. We press down is drawing becomes true. We add one particle, and if we are moving, and we are drawing, we will add a particle. But you'll realize that there's an issue with this, because if I'm moving, let's say within this small square, there are going to be multiple particles in this square, which is behavior we don't really want, because there are going to be many overlapping sand particles. So what we're going to do is, before we add a particle, we will check if, let's create another for loop for particles for every particle in the particles array. If, let's create another variable here, let's call it should add particle, and let's set it to true. Then if the particle's x position is equal to this particle that we're adding's x position, and the particle's position is equal to the particle that we're adding's y position, then we should set should add particle to false and break out of this loop. Then before we add a particle, we should check if we should add this particle. and if we are going to add this particle, then we add the particle. So basically what we've done here is we are checking if we have a particle at the position that we're drawing in. So for example, if we are here and we've moved here and there's still a particle at this position, then we can't add another particle at the same position. Yeah, that's basically that's basically what we are doing here. So if the particle in the particles array is equal to the current particle that we are adding's position, particle, there's another typo here. If we have a particle at that position, then we should add particle to false, then we don't add that particle. So now we won't really have any particle overlap, so we can now press and move the button, and there's another bug. Particle P, I should just reload this and it should work. So now we can see that we can draw multiple sand particles at a time, but you'll see that it's very laggy, and that should be probably because of this. Yeah, that should probably be because of this. We are calling pen fill so many times, which causes it to lag a bit, and we should move these things around a bit. Let's begin the path once, then call fill for each rectangle, and it's still laggy, and it's still lagging for some reason. Or let's just move pen fill outside, and now we can see it's less laggy but still very laggy. But you can see it's basically working. But if you want to optimize this, you probably do this by yourself. Maybe I'll implement one more feature where you can give this random colors. Then I'll call this the end of the video. Then I'll end the video. So we are going to create random. Let's create random colors for each of these particles. So function, let's create a function to get a random integer. We'll use this to get a random integer between 0 and 255, but for that we'll just use return the floor of a random number multiplied by the maximum number minus the minimum. This is how you create a function to draw to get a random number between a minimum value and a maximum value. So for this, once we have this, we'll create another function. Let's call it get random color, and then we will return a formatted string with RGB of a random integer between 0 and 255, and another random value between 0 and 255, and another value of between 0 and 255. So basically what we've done here is we are creating a random RGB value between 0 and 255, 0 and 255, 0 and 255 using this get random integer function that we've implemented. We're going to create a random value. Then here, once we add a particle, we are going to, let's move here and maybe create another property. Let's call it color, which is get random color, which is a value from this. Then before we fill a rectangle, let's call the pen's fill style is the particle's color. I think this should work. So yes, it's working, but there's still an issue here. So I think the issue should be me moving this there. Nope, still an issue. Let me move that there. And it's working. We are drawing particles with different colors, and we can probably hide the grid. Let's see how it looks like without the grid. Okay, it's running smoother. Yeah, this is working fine. You can probably optimize this during your own practice if you want. I'm going to stop the video here. I won't really optimize anything, and I will also leave the link to the GitHub, so if you want to look through the code for this, you'll find it there. And yeah, I think I'm done with this video. You have a sand simulation with pure JavaScript. So if you like this video and you would like to see more tutorials, please hit the thumbs button, comment down below, and if you have any suggestions for tutorials I might do in future, also feel free to leave them down in the comments. And yeah, if you make any project with this that you might want me to see, or you might want the world to see, also leave them in the comments. And I don't think there's anything much more for me to say. Yeah, GitHub, yeah, you can leave the link in the comments. And yeah, so this is the end of this video. Goodbye. We shall meet in another tutorial and another challenge. So yeah, if you have any other challenges for me, yeah, I will do them. Leave them in the comments. So hello again. So yeah, I thought I was done with the tutorial, but there are actually minor fixes I wanted to make, or was done, but yeah, I want to fix a few things. First of all, I want to change this to 8 so that the particles appear smaller. Then you'll notice that when we run the simulation and we add a particle, the sand particles move slightly faster than when we are not adding a particle. So I want to fix that. And how we're going to fix that is we'll create another function called render, and we'll call this render, and we'll move all of the code for rendering stuff to that line. So I'll just take this, move it down here. Then, oh, by the way, if you want to know what happens if we don't clear the screen before we add a new particle, this is what happens. Okay, I did not call render. So render, let's call render, and now you see what's happening here. The particles are smearing themselves on the screen instead of like actually looking like moving particles. They look like smearing blobs. So you have to clear the screen so that they'll actually look like they're falling down. But then you notice that we still have that problem where they move faster when we're adding a particle, and for that we'll come here to the add particle function and we'll remove update and instead call render, so that we just show the particle instead of updating stuff. So now when we add a new particle, they all move at a constant speed, but they move at a constant speed and they're moving too slowly. And to fix that, I will just come here and maybe change this to 50 so it will look smoother. Yeah, this is so much better than what I had before. If you want it to look faster, to move faster, maybe you can change that to 20 or something smaller so it can look something like this. But I like it looking like it's staggering a bit or like it's lagging a bit. It looks kind of nice like this. So yeah, those are the fixes I wanted to make. So now you have your almost perfectly functioning sand particle simulation. And if you want to play with this and add stuff, feel free to do so. And then you can leave your stuff you made with this, your projects and whatever you made with this, down in the comments. I will look through them and yeah, might showcase them in a short or something. So yeah, this looks nice and it does what we expected it to do. So this is the actual ending of the tutorial. Goodbye.